So we've talked about a lot of components of lateral trim and stability, and now we're going to bring these together in some general solutions. And we're going to start off with a small angle lateral trim solution, okay? So laterally, our requirement for trim is that the summation of forces in the y direction has to be equal to 0. The summation of moments about the x-axis have to be equal to 0, and the summation of moments about the z-axis have to be equal to 0. And so I'm just going to write this in a general form here, where we're going to have the change in y coefficient with respect to beta multiplied by beta plus the change in y with respect to delta A times delta A plus the change in y with respect to delta R times delta R. So this is all my forces in the y direction, okay, this first line here. So we have some force due to beta, some y force due to delta A, some y force due to delta R. We can also have some y force due to the propeller, even at 0 beta, delta A, or delta R. Okay, so let's say this is some y force from the propulsion system or the propeller. And then finally, we also have a force in the y direction due to our bank angle. Now, the force in the y direction due to bank angle would be W times cosine of theta, where theta is my climb angle, times, elevation angle, times the sine of phi, which is the bank angle. And for small elevation angles, we can say that this is just W times sine of phi. And then if we're assuming small bank angles, then this is just W times phi, okay? So anyway, you'll usually see one of these two here in this last slot. So we're going to say, and we're putting this in coefficient form, so once we take the weight and non-dimensionalize it by the dynamic pressure in the area of the main wing, then we get a CW times, I'll put in the sine of phi, okay, assuming we won't necessarily assume a small bank angle here. So all of that has to equal 0. So that's our force in the y direction. We've filled out our first row here. That's the force in the y direction. Now let's look at moments about the x-axis. In non-dimensional form, what we'd have is a change in rolling moment with respect to beta times beta, plus a change in rolling moment with respect to delta A times delta A, plus a change in rolling moment with respect to delta R times delta R. And we'll also have we can have some rolling moment due to the propulsion system. And then our bank angle here actually does not factor into the rolling moment because that the force from gravity acts through the center of gravity. And so again, all of that has to sum to 0. And then we can so that's our rolling moment, and now we can look at our yawing moment. We'll have some Cn beta, Cn delta A, Cn delta R. We can have some yawing moment from the propulsion system. And then again, this is 0, and that has to sum to 0, okay? So these are what we're going to call our small angle lateral trim equations. Now, small angle is referring to a few things here. We've assumed that our elevation angle is small. We've also assumed that beta, delta A, and delta R, all of these are angles, that they are small enough to remain within linear aerodynamics. So linear relationships between these forces and moments and these angles, okay? And those are pretty good approximations for most of the maneuvers that you'll ever experience in an aircraft. These are relatively small. Now, I haven't used the small angle approximation here. We could just swap out a phi here, because sometimes you might want to trim this aircraft in what's called the knife edge, where you're banked 90 degrees. Still, your beta, delta A, and delta R are probably still going to be small enough to use these small angle approximations, but your bank angle then, of course, is much larger. So this is the way I like to look at these equations here. But still, these are small angle lateral trim equations because we've assumed most of these things are small. Okay, so let's just talk through these really quickly. So this first column here are stability derivatives. These are changes with respect to beta. And then these last 6 here are what are called control derivatives. Now remember, our control derivatives, we have some primary derivatives and then some coupling derivatives. So for example, CLDA, that's a primary derivative. When we deflect the aileron, what we're primarily hoping to get out of that is a change in rolling moment. But by deflecting the aileron, we're also going to get a change in yawing moment. So this is one of these coupling derivatives. And then CNDR, this would be a primary derivative. We're deflecting the rudder to get a yawing moment primarily. But when we do that, we'll also get some change in rolling moment. So these two are kind of our coupling terms, and then these two are the primary control derivatives there. Okay, so what we see here is we've written this in a form where the pilot is going to choose delta A and delta R, and then beta and phi are actually 2 other variables that he doesn't have direct control over, but the aircraft, as long as it's stable, will trim out. Once he's deflected delta A and delta R, it will trim out to some beta and phi that then satisfy these equations, right, for us to be trim. So what we see here is we actually have 4 unknowns. We have a phi, a beta, delta A, delta R. We only have 3 equations. So there's actually an infinite number of solutions to this. And again, the pilot is only choosing delta A and delta R, but there are multiple combinations of those that will satisfy these equations. And any combination of these 2 will then result in a different beta and a different phi that are required to satisfy these equations, okay? So actually, what's nice about this is we actually get to choose what we want beta or phi to be, and then that will tell us what delta A and delta R need to be in order to satisfy that, okay? So it turns out that there are an infinite number of solutions to this, and we get to choose an extra value or a value for one of these extra variables, okay? So let's talk about some of the benefits of choosing a certain value for beta. So let's say that we want beta equal to 0. That means that we have 0 side slip, okay? So the benefits to this are that is a minimum drag solution, and it also results in, most of the time, best passenger comfort. Okay, so if you're concerned about your passenger comfort, which they often are on airliners, and of course they're also concerned about minimizing drag to conserve fuel, then often they'll choose the beta equals 0 solution to this. And so basically what we'll do is, and we'll get to this later, but we can rearrange this equation so that beta is not in this vector here. We can set that equal to 0 and swap it out for phi, and we'll instead be solving for phi, delta A, and delta R for that solution. Okay, so when would you not want beta equal to 0? When would we want to instead choose phi? Maybe we want to choose phi to be exactly 0, or maybe we want to be very specific about the bank angle that we're trimming at. In that case, we're going to set phi, and we're going to solve for beta, and most likely get a non-zero beta. So there are a couple examples when this is useful. One of those is in what's called a crosswind landing, and we'll talk about that example in more detail. Another is in formation flying. So if you have, if you're trying to keep your wings level and maneuver relative to another aircraft without banking your aircraft, if you need to move right or left and you don't want to bank the aircraft because you're in some tight formation, that's another time when that might be important. Another is aerial refueling. So often you'll need to maneuver a fighter aircraft, for example, a small aircraft relative to a larger aircraft, and you're maneuvering through tight spaces so that are very carefully and coordinated so that you don't get into the wake of that of the larger aircraft, because that can be extremely detrimental. And then we also have cases in acrobatics, and finally sailplane towing. And this is kind of like the aerial refueling example, where you have an aircraft that's closely oriented next to another aircraft, and you need to maneuver those relative to each other. So anyway, so there you go. So those are some examples of when you might want to choose beta equals 0, or maybe you want to set your bank angle instead. Now, one other thing that this equation points out is that because we have an extra unknown here that we can choose, either beta or phi, we can actually get rid of one of our control surfaces in some cases. And so in the radio-controlled world, oftentimes they will get rid of an aileron deflection. And so the way that they then control roll is through a rudder deflection. A rudder will get the aircraft. It can create some rolling moment itself, as we've talked about, but mostly what it creates is a side slip, beta, and then through the dihedral on the wing, once we get beta, that will create a rolling moment. And so so a lot of RC aircraft will do that. So usually those are what are called 3-channel aircraft. So what they have is a 3-channel aircraft. What they have is a delta E, their elevator deflection, delta R, their rudder deflection, and then a throttle. And so anyway, this simplifies the aircraft just a little bit. Instead of carrying 4 channels, they only carry 3 channels, and they're still able to bank the aircraft and fly it around. So anyway, so this is our small angle lateral trim. These are the fundamental equations, and now we're going to look in the next couple videos of different ways to manipulate these equations to learn things about certain solutions.